So today we are going to learn about carbocations. Carbocations formation and stability. So carbocations are the base of the organic chemistry, I must mention, because carbocations are like the foundations of organic chemistry. If you want to learn the reaction mechanisms, you want to learn about the name reactions, if you want to learn about the reagents, so you should know what the carbocations, how they are forming, what's the stability parameters, and most important is how you are going to proceed forward in the reaction. Only this will let you know about the complete reaction mechanism process, and the carbocations will guide you in the process, like how you have to proceed further in a particular reaction. As you all know that the reaction mechanisms, or I must say the name reactions, usually consist of 3 to 4 steps. So how you are going to proceed further, like after first step you have to go to the second step, after the second step you have to go to the third step, and after the third step you have to go to the fourth step. So how this can be possible? This can only be possible with the help of the carbocation. So carbocation gives you an insight so that you can move forward in the reaction mechanism. This is the most simpler carbocation you can ever see in your organic chemistry is this particular carbocation. This is another carbocation. This is also carbocation. This is also carbocation. This is also carbocation. And this is also carbocation. So in organic chemistry, all over the book, either you can take reference from Mettler and Jones, you can take reference from Claydon, you can take reference of Paula Bruce, or you can take reference from your whatever book you like. For example, Peter Sykes, Mettler and Jones. In each and every organic chemistry book, the most important topic is organic chemistry. I have taken the reactions from the Mettler and Jones as well and from Claydon as well. So you can refer both the books for your preparations for different competitive exams. So you have to consider the carbocation topic very seriously, because it's the base of the organic chemistry. From this particular topic we will move forward with carbon ions, and from that carbenes, nitrines and benzenes. So carbocation is a reactive intermediate. Carbocation is not a product, not the reaction. You have to learn this. Carbocation is neither the reactant nor the product. Carbocation is neither the reactant nor the product. So you have to mention this. You have to understand this. Carbocation is neither the reactant nor the product, but the carbocation is the reactive intermediate. Carbocation is reactive intermediate because if we are moving from reactant and product, the reactant is represented as R and the product is represented as P. So if the reactant is converted into product, so in between these, any of the step, there is a chance of formation carbocation, carbon ion, nitrine, benzene, carbon. So there are chances of formation of reactive intermediates. Each and every reaction in organic chemistry proceeds via formation of a reactive intermediate that can be carbocation, carbon ion, nitrines, carbenes, benzenes. There are high chances of the reaction mechanism in which the carbocation is a reactive intermediate, because if nitrine is forming, also carbocation is also forming somewhere. So we cannot say like in a particular in a particular organic chemistry reaction, if a reactant is converting into a product, there are only chances that only one reactive intermediate is formed. That is not necessary. 2 or 3 reactive intermediates can be formed in a particular reaction. So you have to consider this topic of reactive intermediates very carefully, because it usually consists, or you can say it's a base of reaction mechanism. So you should know what are the types of the reactive intermediates, and from reactant to product, how the reaction is going on. Which product is forming, which is major product, which is minor product, which is more stable, which is less stable. All of these particular questions you get to know about the reactive intermediate, because the reactive intermediate formation as well as the stability will guide you so that you can form a product from a reactant and the reagent. You only get to know if you have a reactant A and your product is P, and we have certain set of reagents. So you have to draft that particular mechanism from first step, from second step and from third step, and you have to go to this particular target with the product. So the product is your target. So you have to achieve that particular target. So you have to go from the series of reactions, and that reactions, like from, if I'm saying A is converted into P through 3 steps. So it's a 3-step reaction. So in first step, A is converted into some X. From X is converting into some Y, and Y is converting into some P. Y is converted into P. So this is a series of reaction. So what is X, what is Y, which is more stable, which is less stable? Because in the organic chemistry we have 2 types of products, sometimes major and minor. Which product is major, which product is minor, you will get to know about from the stability as well as the amount of the products from the concept of reactive intermediates. So the reactive intermediates is very, very essential in organic chemistry. There are different types of carbocation. These all are different types of carbocations. These all are different types of carbocations. It can be represented as C with a positive sign. Now you have to consider this particular example. In this particular example, you have a carbocation. In this carbocation, I have drawn the orbital diagram of carbocation. In this orbital diagram of the carbocation, what you have to do is, you have a top view and the side view. You just have to clearly see the structure in which we have the sp2 carbons. Why? Because we have 3 sigma bonds. Why I'm saying this? Because we have 3 sigma bonds like this. We have a carbocation, suppose we have CH3. We have CH3. So we have CH3. So we have a CH3 here. We have a CH3. We have a carbocation like this. So how we are going to draw this? We have CH. We have CH here and CH here. So we have 3 sigma bonds. And if we have 3 sigma bonds, it means the hybridization is sp2. So the carbon is sp2 hybridized because this particular carbon is 6 electron group. Because CH3, 1 electron of hydrogen and 1 electron of carbon, 1 electron of hydrogen and 1 electron of carbon, 1 electron of hydrogen and 1 electron of carbon. So the total is 6 electrons. So a carbocation, this methyl carbocation is usually a 6 electron species. It's electron deficient. So if the particular group is electron deficient, we have a positive sign here. We have a positive sign here. It means this particular molecule is electron deficient. So that's why we have put the positive sign. We have to put the positive sign on those molecules which is electron deficient. So that's why I have mentioned a positive sign on carbon, because it's 6 electrons. And usually for the octet completion we need 8 electrons. For octet completion we need 8 electrons, but there are 6 electrons, so 2 electrons are less. So that's why we have put the positive sign here. So in the carbocation, that is CH3 plus, in the carbocation, that is CH3 plus, we have 6 electrons and we have 3 sigma bonds, due to which the hybridization is sp2, and that particular orbital diagram is drawn here. So just consider the top view of this particular carbocation. We have sp2, 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 because the carbocation is sp2 hybridized. Because the carbocation is sp2 hybridized, and this is the head-on overlapping, because it's a sigma bond. This is also a sigma bond and this is also a sigma bond. So this is the head-on overlapping between the orbital of hydrogen, that is the oneness of hydrogen, do head-on overlapping with sp2 hybridized orbital of carbocation, of carbon. So there is a head-on overlapping. There is head-on overlapping between oneness of hydrogen. This sometimes in exams questions have been asked related to the name of the orbitals that involves in the overlapping. So you should know the proper names of the orbitals that is involved in the overlapping. So that is, there is a head-on overlapping between oneness of hydrogen with sp2 hybridized orbital of carbon. So this is the name of the proper orbitals which involves in the overlapping in the carbocation. So when the oneness orbital of hydrogen overlapped, head-on overlapped with the sp2 hybridized orbital of carbon, then we can say this particular bond is formed. So this is the proper way of mentioning the bond formation. So this is the top view of carbocation and this is the side view. In this we have a vacant p orbital, because two electrons, we have the deficiency of two electrons, and if we have the deficiency of two electrons, it means that we have one vacant p orbitals, because this particular p orbitals can occupy two electrons. So this is the top view and this is the side view. So when there is a top view and the side view, so you can clearly see what's the difference. So you can clearly see that in the carbocation there is the 2 electrons, that is less, because for the stability we should have 8 electrons in the octet, and in this we have only 6 electrons. So 2 electrons are less, so we have a space for 2 electrons in our molecule, because we have a space for 2 electrons. Now there are different types of the carbocation. I have mentioned you about the methyl carbocation. First of all, I mentioned you about the methyl carbocation. That is this. So this is a methyl cation. This is very least stable. So we have sometimes we have ethyl. When we are going to add a substituent on this, so this is a ethyl carbocation. And if I'm going to add the substituent on both the chains, so this is isopropyl carbocation. And if I'm going to add the substituent on all the three sides, then this is a tertiary carbocation. So we are talking about the stability of carbocation. So the carbocation can be stabilized by various electronic effects. So stability of carbocation can be achieved by various electronic effects that can be inductive effect, that can be hyperconjugation, that can be resonance, that can be aromaticity, and that can be mesomeric effects. So we have 5 electronic effects that are responsible for the stability of carbocation, or I must say stability of reactive intermediates. So stability of reactive intermediates can be achieved by the different electronic effects: inductive effect, hyperconjugation, resonance, aromaticity, mesomeric effect. So the first effect that we have to prioritize is aromaticity. After that we have to prioritize mesomeric effect. After that resonance, hyperconjugation, and inductive effect. So this is the order of priority for the different effects: aromatic effects, mesomeric effect, resonance effect, hyperconjugation, and inductive effect. So these all are the effects that we usually studied in our 11th 12th classes. I am going to do a quick revision of these particular effects.